Hi everyone, Professor Krishna here. Um, I hope that everyone is staying safe and and is taking care of themselves. I'm pretty much holed up in my house, so what I'm going to do from here on out is I'm going to be putting up a series of videos which will take the place of our in-class lectures. I will give everyone instructions on Blackboard for how to do the remaining components of this class, like homeworks and labs and tests. But I have mostly figured out how to take care of the rest of this class for the rest of the semester. We're going to be treating this as a purely online class. To begin, we'll review the definition of work. Work measures the practical impact of a force on an object. Work is calculated as the dot product of the force vector and the displacement vector. Let's first revisit how to calculate a dot product. A dot product is an operation that is done on two vectors. If the two vectors are in Cartesian, you calculate the dot product by multiplying the x components of those vectors, then multiplying the y components, and then adding the two products together. So for example, here we have one vector, 2i plus 3j, and a second vector, 4i minus 5j. The dot product is calculated by taking the x components, 2 times 4, and then multiplying the y components, 3 times negative 5, and then adding them together. This yields 8 minus 15, which is equal to negative 7. So the dot product of these two vectors is negative 7. In the more likely case that the two vectors are in polar, the dot product is calculated differently. We take the size of the first vector, multiply it by the size of the second vector, and then multiply that by the cosine of the angle between the two vectors. In this example, the first vector has a length of 3 and is oriented at 30 degrees. The second vector has a length of 4 and is oriented at 100 degrees. So the dot product is calculated as 3 times 4 times the cosine of the angle between them, which is 70 degrees. That works out to 4.1. So the dot product of these two vectors is 4.1. Now, let's return to the definition of work. We can rewrite the equation for work like this. Work equals the size of the force multiplied by the size of the displacement multiplied by the cosine of the angle between them. It is extremely important to note that work is a very unique quantity in all the physics we've seen so far. Work is one of the few quantities that is a scalar, not a vector. It is one of the very few quantities that we've seen so far that has no direction. Let's look at a simple case. Here, a 5 Newton force is applied to a box. The force is pointed in the positive x direction, so its orientation is 0 degrees. The object displaces 2 meters in the positive x direction. The orientation of the displacement vector is also 0 degrees. We can calculate the work using the equation we used earlier. Work is the dot product of force and displacement, which in turn equals the size of the force multiplied by the size of the displacement multiplied by the cosine of the angle between them. Substitute the values of force and displacement into this equation. The force had a magnitude of 5 newtons, and the displacement had a magnitude of 2 meters. Both the force and the displacement are oriented at 0 degrees. The work is easily calculated. 5 newtons times 2 meters times the cosine of 0 minus 0 yields 10 joules of work. Now, what if the force was not aligned with the displacement? Suppose the force vector is oriented at 30 degrees above the horizontal. The work would now be calculated like this. The displacement is oriented at 0 degrees, but this time the force is oriented at 30 degrees. Simplifying, the work is now equal to 5 newtons times 2 meters times the cosine of negative 30 degrees. That works out to only 8.66 joules of work. So the greater the angle between the force and the displacement, the less work the force actually does. At this point, you're probably wondering if there's such a thing as negative work. The answer is a resounding yes. For instance, suppose you lift an object that has a weight of 30 newtons a distance of 1.5 meters. The weight force is pointed downwards, which means its orientation is 270 degrees. The object's displacement is 1.5 meters upwards, which means that the orientation of this vector is 90 degrees. Substituting the values into the equation for weight, we end up taking the cosine of negative 180 degrees, which is negative 1. So the work done by the weight force is negative. A negative work always occurs when the force acting on an object points opposite the direction of motion. Obviously, if an object doesn't move, its displacement is 0, so the work done by the forces acting on it is also 0. But consider this situation. A 20 Newton object is carried at a constant height over a distance of 3 meters. The weight vector has a size of 20 newtons and is oriented at 270 degrees. The displacement has a magnitude of 3 meters and is oriented at 0 degrees. The work is equal to 20 newtons times 3 meters times the cosine of 0 minus 270. But the cosine of negative 270 is 0, so the work done by the weight force is also 0. Whenever a force is perpendicular to the displacement, that force is doing 0 work. This can be seen in circular motion too. The moon moves around the Earth in a roughly circular orbit. The motion of the moon is always tangential to that circle. However, the force that it feels from the Earth is the centripetal gravitational pull from the Earth. The force, in this case, is perpendicular to the direction of motion. In fact, it's always perpendicular to the direction of motion. So in circular motion, there is no work done. To summarize, work is the tangible effect that a force has on an object. It is calculated as the size of the force multiplied by the size of the displacement multiplied by the angle between them. The greatest amount of work occurs if the force is exactly aligned with displacement, that is, if the angle between the two vectors is 0. At larger angles, the work decreases. At 90 degrees, the work is 0, and above 90 degrees, the work is negative.